All right, in this tutorial, we're going to figure out how to determine which pKa to use if you have a polyprotic acid and you have to do a calculation with Henderson-Hasselbalch equation, right? So let's start with HH. Henderson-Hasselbalch equation says that pH of solution depends on pKa plus log of ratio, deprotonated form, A minus, over HA protonated form. And the A minus and HA are kind of abstract things. You can talk about generic weak acid, which is we represent as HA. When it loses proton, it has conjugated base A minus and the proton, right? So our pKa is acid dissociation constant for this kind of equilibrium, but in a log form, right? So if you remember, pKa equals to negative log of Ka, where Ka is the acid dissociation constant. All right, so the first thing, in order to figure out which pKa to use, you got to know what are all the ionization forms of the acid. And the one that people are often confused is the phosphoric acid. And so we need to start with like drawing it fully. So this would be H3PO4, right? And this one can dissociate a proton. So if it loses a proton, it would have one negative charge, O minus, and then the rest is still OH. And then it can lose another proton, P O minus, O minus, OH. If you remember, then negative charges in the H can kind of move around this molecule through resonance. So we have one more pKa where it loses all of the protons, O minus, or O minus. Okay, so this would be PO4 3 minus, HPO4 2 minus, dibasic, and then H2PO4 minus. Okay, so these also, like in your problems, you might see instead of H2PO4 minus, you might see it as sodium H2PO4 minus, no minus here, sorry. Let me get rid of that. Sodium H2PO4 is dissolved in solution to make, say, a phosphate buffer, right? So the reason for that is this negative ion that has O minus could have ionic interaction with the sodium plus, and this salt is what usually like how phosphate comes in. And then when it dissolves in solution, it falls apart completely, so you don't see the sodium, right? For this ionic compound, we only care about the weak acid. And so if in your problem you have H2PO4 and HPO4 2 minus, I would recommend immediately relabeling them as HA, and so this would be HA, this would be A minus, and the pKa that's between the two forms, in this case it's going to be 7.2, that's the pKa you have to use in your calculation using, so like here in the Henderson-Hasselbalch, right? If you start, on the other hand, with phosphoric acid and monobasic phosphate, then for phosphoric acid, this is HA, the monobasic phosphate is then A minus, and the first pKa, which is like 2 point something, I don't remember now, this pKa is the pKa you would use in your calculation, okay? And so following kind of this logic, right, if you start with dibasic phosphate and tribasic or just phosphate ion, PO4 3 minus, then this would be HA and this would be A minus. And this pKa is somewhere around 12, I think, pKa. The third one is around 12 point something. All right, this may feel a little disturbing, right? Because, well, who is A minus, who is HA? Why is this switching? And so think of this as like which molecules plays a role in the performance, like in the play or something like that. So the pH is closer to, say, pK of 2, then we have two forms that are predominant forms in solution, and then we use that pKa. When pH is closer, let's see, I'll put it on green. pH is closer to 12, so say we're working with pH 3, pH 11, pH 10, right? Then the dibasic phosphate plays the role of HA. But then if the pH goes close to 7, that same molecule now, it's no longer losing the last proton. Now it will be losing one of like this other proton, right? So that's why this like shift. All right. I feel like I should mention one more thing that might be helpful to you in these problems. So remember our titration experiment. And when we do titration, the titration graph usually looks something like this. So on this side, we're going to have base added. And often we talk about equivalence of hydroxide added. That just means per mole of solid, like per mole of some kind of acid, number of moles of hydroxide, OH minus, right? So that's what OH equivalent is. Okay, and so on this side, we're going to have pH, and then we can start thinking that when we get to the flattest part, right, that's going to be pH equals to pKa. And we know based on Henderson-Hasselbalch reaction that at that point, concentration of HA equals to concentration of A minus, okay, at that point. But then if we go lower, what's going to be my lower? So if the pH is lower, we're going to have more HA, and the pH, when pH is higher than pK, we're going to have more A minus. And that goes back to this idea that there's an equilibrium, A minus plus H plus. So at low pH, like say down here, at low pH, we have lots of protons around. And so when I have lots of protons, it's going to push the equilibrium towards more HA. And that's why I have more HA here, right? And then at high pH, it sort of goes the other way. When the pH is high, right here, in this part of the curve, there is fewer protons around, so the equilibrium shifts towards losing protons or giving up protons, right? Then we have more A minus. So hopefully that's going to be helpful for you. Good luck with the problems.